Good morning, friends. In today's lecture, we will take up part two of the impact of free jets. I divide the impact of free jets into three parts. The first part consists of the cases related to the fixed plate, whether it is held normally or inclined, or a curved plate or vane, where the jet strikes at the center, where the jet strikes at one end, symmetrical, unsymmetrical. But all these five cases, the plate or vane is fixed. So in all these five cases, we have calculated the force. The work done is equal to zero because the plate velocity or the vane velocity is zero. So that's where we have completed that portion. And in the previous lecture, we have taken up some problems related to that part. In part two, again, I divide into three or four lectures wherein we discuss on the moving plates or moving vane. Maybe a flat plate held normally, which is moving with a velocity v, u, an inclined plate moving with a velocity u, or a curved plate or a vane where the vane moves in the direction of jet at a velocity u and is symmetrical. So these three cases where the plate or vane is moving, we will take up. And once after taking it up, what is the problem with a single plate or vane moving? How to overcome that problem, that we see at the end. So that is what the solution for that is: the series of vanes, the series of plates mounted on a wheel. So that we will do in three or four lectures along with some problems. So that completes the part two. So today we are at the beginning of that part two, where we are discussing in this lecture when a flat plate is moving with a velocity u and a jet is striking normally that flat plate with a velocity v. What is the proposition? How to calculate the force? And once the plate is moving, the other thing that comes into picture is work done. How to calculate that work done? So these are the two things in the case of flat plate held normally. Once I tell that, naturally, you also can do for inclined plate if it is moving. So these two cases, we will do it in this lecture and then basically move forward. So let me take you directly to the whiteboard wherein we straight away discuss on that. Thank you. So friends, our part two is force exerted by a jet on a moving plate or vane. This is our topic. And there are three cases in this. One is force exerted by a jet on a moving flat plate held normally. Force exerted by a jet on a moving flat plate kept in inclined position. Force exerted by a jet on a moving curved plate, which we call it as vane, which is of course symmetrical. Jet striking at center. So these are the three cases which we will take it. Out of that, A and B, today we will take it up, and then actually the next C part we will take up in the next lecture. So now directly I will go. Force exerted by a jet on a moving flat plate held normally. How it looks like. Suppose this is the flat plate, right? If I draw the center line, this is the center line. So now what is the thing? The jet is striking like this, but this is moving with a velocity u. This jet is coming with a velocity v. So now if it is moving with a velocity u, after some time, this plate position is, this is the position of the plate. So the jet has to travel like this and strike. Now the question is how to solve such a problem when the plate is moving actually. So if the velocity of jet is v and velocity of plate is u, do you expect that the jet, the whole jet with a velocity v will strike the plate? If it is fixed, it will strike. But if it is moving, the whole velocity, which we call it as absolute velocity of jet, the whole velocity of jet, the whole basically what you call it as the mass of water which is released from the nozzle, will it strike the plate? No. The reason being, by the time the jet comes to the plate has already moved by a distance u in 1 second. If suppose this mass, which we call it as rho AV, by the time it moves near to the plate is not there at all. The plate has already moved by a distance u. Naturally, if this mass has to strike the plate, now it has to overcome that velocity and go. That is why the effective velocity with which the jet strikes the vane is not v. It is something actually different from this. So that's why we use the terms actually v is equal to absolute velocity of jet. What do you mean by absolute velocity? The jet which is leaving from the nozzle with a velocity v, whereas u is the velocity of plate. A is the cross sectional area of jet. Right now, how to do it? If suppose this jet has to strike the plate and and has to apply some force, naturally how this type of problems are solved is, what we do is, for the whole system we consider this entire system as one. And for this system, if you apply all imaginary, you imagine that for this system, if you apply a velocity u in the opposite direction, now you tell me what is the final picture of this. Suppose plate is moving with a velocity u, jet is moving with a velocity u. Now for this whole thing, I have applied actually, I'm imagining, I'm not really applying it. I'm only just trying to understand or trying to analyze this whole picture, how to calculate. So that is why I try to apply a velocity u in the opposite direction. So when I apply velocity in opposite direction, so naturally, what will happen to the plate? So I applied on the plate itself like this. So if I apply like this on the plate, so the whole plate velocity finally it becomes what? It becomes nullified, right? But remember now there are two velocities. One is velocity of jet in the positive direction of x-axis, the velocity of vane in the negative direction of x-axis. Am I right? Then only it appears as if it is stationary. So by the application, but means this is what I am imagining. Why I did that? Because I want to know the effective velocity. So this principle of applying basically a velocity opposite to it and thereby bringing the whole system into standstill, and as if it is a fixed flat plate, applying the principles and doing the problem is what we call it as that is the only way to solve these problems. So what type of principle I have used? The principle which we know long back actually at the early stages in basic in physics or mathematics, that principle of relative motion I have used actually. Principle of relative motion. Applying this principle, right? Now I calculate what is the effective velocity of jet. Effective velocity of jet is v is the velocity of jet minus u is the velocity of the plate. Why minus? Actually, I imagined that for the whole system, I have applied in the opposite direction so that the system becomes a standstill. The for me, for a moment, it happens that it is a fixed plate. So applying that principle of relative motion, I calculated what is the effective velocity of jet. So that means actually the velocity with which the jet is suppose is striking the plate is only v minus u. It is not with v it can strike. The reason being it is not fixed plate. It is moving with a velocity v. To overcome that, to overcome the velocity of the plate, so the effective velocity with which the jet strikes the vane is or the plate is v minus u. So this is one of the things that you should remember. Therefore, now in all the proper in this part to kindly remember, v is only the absolute velocity, v is not the effective velocity. If the moment the plate is start traveling, the immediate thing is you should remember the velocity with which the jet strikes the plate is deferred, is the effective velocity. How to calculate that effective velocity? Apply the principle of relative motion, because the jet is moving in the x direction, plate is also moving in the x direction. If both are in different directions, That I will come back in part 3, what will happen. So don't worry right now. So right now, as both are traveling in the x direction, so naturally we apply the principle of relative motion straight, and then we got this effective velocity. Whether it is a single flat plate, or whether it is flat plate held normally, or it is held basically inclined, or it is curved. In whatever case, the whole velocity with which the jet is emanating from the nozzle will not strike the plate or the vane. It is only with the effective velocity it strikes the plate or vane. That effective velocity has to be calculated. So that's what we have done. So therefore, mass per second, mass of fluid striking per second is equal to, we know, rho a into effective velocity, because now no more v is valid. So it is rho a into v minus u. That is next thing. So this is mass is over. Then naturally, what is initial velocity? Initial velocity in the direction of jet is equal to, that is effective velocity v minus u. Then final velocity in the direction of jet is equal to 0. Why 0? Because the jet actually leaves tangentially, right? This is the thing. Therefore, applying impulse momentum equation, force is equal to mass per second into initial velocity minus final velocity. Remember, if you are taking force in one direction, initial velocity, final velocity also should be in the same direction. So therefore, the force means force exerted by the jet is equal to mass per second is rho a into v minus u. Initial velocity is v minus u, final velocity is 0. So rho a into v minus u whole square. So once again, I will summarize. If you take a fixed flat plate held normally, F is equal to rho a v square. Whereas moving flat plate held normally, F is equal to rho A into V minus U whole square. But in this case, the work done is equal to 0. But here, work done per second is equal to F into U. F is rho A V minus U whole square into U. So kindly note this. So this completes to me the first part in this today's lecture. The second one is what is case 2, which we are interested. What is case 2? Force exerted by a jet on an inclined moving plate.
So draw the figure first. Draw the center line. So this is the inclination. Now the moving plate we talked about, draw the picture. This is the position. By this position, this is moving with a velocity u. A jet strikes with a velocity v, right? The jet actually, if you take it, y dotted I am talking is imagining. So this is v minus u. Already I explained. This is v minus u. Already this case we have solved previously. How we do it? We do normal, calculate normal force, and once normal force is calculated, then we calculate basically fx and fy. So how to calculate the a normal force, that we take it. So already you know it. What is the remaining things I am avoiding again repeating. So again, absolute velocity of jet is v, velocity of wave plate is u, the angle of inclination is theta. So directly, if I come to the point, what is the effective velocity of jet? Is equal to v minus u. That is first step. Once that is over, then what is the mass of fluid striking per second, rho a into v minus u. This is over. Once this is over, then naturally we are calculating in the normal direction. So write in the normal direction initial velocity. Actually, in x direction, initial velocity is that is initial velocity means effective velocity. I mean, so v minus u. But in the normal direction, when I am taking it, it is v minus u sine theta. This is in the normal direction. What is the final velocity? When I am writing, please remember it is only 0 because the jet is leaving tangentially. There is no velocity in the normal direction. So therefore, applying impulse momentum equation, applying impulse momentum equation, force exerted by the jet in the normal direction, because we are calculating in that only. Normal direction is equal to mass striking per second initial velocity in normal direction minus final velocity in normal direction. Therefore, Fn is equal to rho a into v minus u. This is mass. Initial velocity is v minus u sine theta. Please remember why sine theta has come is we are taking the velocity component in the normal direction. So therefore it is rho a into v minus u whole square into sine theta. This is the first thing. And I want fx and fy. What is fx is equal to? It is fn sine theta. So which is equal to rho a into v minus u whole square into sine square theta. Fy is equal to Fn cos theta. So therefore it is rho A into V minus U whole square into sin theta cos theta. Okay. So if you compare it with the previous one, for example, you take it fixed plate in inclined position, moving plate in inclined position. Fn is equal to rho A into V into sin theta, rho A V square into sin theta. Fn is equal to rho A into V minus U whole square into sin theta. Fx is equal to rho A into V square into sin square theta. Fx is equal to rho A into V minus U whole square into sin square theta. Fy is equal to rho A V square into sin theta cos theta. Fy is equal to rho A into V minus U whole square into sin theta cos theta. Work done is equal to work done is equal to 0. Work done is equal to work done per second. Fx into U. Please note down this. Fx into U. So therefore work done per second is equal to rho A into V minus U whole square sin square theta into U. So this completes to me the first two cases. So I will stop my lecture at this place and we will take the third part in the next class in the next class. So, friends, in today's lecture, I have completed a moving flat plate held normally. What is the force? What is the work done? Similarly, a moving inclined plate, right? What is the force? What is the work done? Kindly note the things clearly, and there we will stop the lecture today. And next class we will meet again. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.